In today's lecture, we're going to talk about counting distributions where we're putting balls into boxes, but we're going to be focusing specifically on those distributions where we leave no empty boxes. So the main question we're going to be asking today is, how many distributions are there of m distinct balls into n distinct boxes with no box left empty? Here's an example. How many ways can we put 5 balls into 3 boxes? These are distinct balls into distinct boxes with no box empty. In order to answer that, one approach is to just ask what types of distributions are allowable. And when I talk about the type of a distribution, I mean what we talked about in a previous lecture. We have 5 balls, ball 1, 2, 3, 4, and 5, and they're going into 3 boxes. Say box A, box B, and box C. And when we talk about the type of a distribution, you might have a distribution of type, for example, 1, 2, 2. That would be a distribution of the 5 balls where we put 1 into box A, 2 into box B, and 2 into box C. That would clearly be an allowable type of distribution since no box would be empty. If we had a distribution of type 2, 0, 3 to put the 5 balls in with 2 in A, 3 in C, none in B, that one we're excluding and we're not going to be counting that here. So, what are all the allowable types? Well, as we already said, one of the allowable types with no box empty is 1, 2, 2. We need these 3 numbers, the number that go into A, the number that go into B, and the number that go into C. They all have to be at least 1, and they have to sum to 5. Well, one way to do that is 1, 2, 2, but we could rearrange that. There are 3 different rearrangements that will also be allowable types. This would correspond to 2 balls in box A, 1 in B, 2 in C. And then, of course, there would be 2, 2, 1. So we have 3 different types that all kind of look similar. 1, 2, 2, 2, 1, 2, and 2, 2, 1. But there's another type that works. We could put 1 into box A, 1 into box B, and the remaining 3 into box C. And of course, there are 3 rearrangements of this. We could have 1, 3, 1, or 3, 1, 1. And these are all allowable types where we have 5 balls going into the 3 boxes and no box is empty. Now here, just by kind of looking at all the possibilities, I claim there are no other ways to put 5 balls into 3 boxes and have at least 1 ball in each box. Why? Well, if you have at least 1 ball in each box, either one box gets 3 balls, in which case it has to be one of these types at the end, or if you don't have 3 in any box, you have 2 in one box, you'll need 2 in another and 1 in the other, and that will have to be of this type. So these are all the allowable types. Now here's the question: how do we count all the different ways to have a distribution of all of these 6 different types? Well, that's where we have the distribution numbers. So the total is just going to be this distribution number 5, 1, 2, 2, plus 5, 2, 1, 2, plus 5, 2, 2, 1, plus 5, 1, 1, 3, plus 5, 1, 3, 1, and finally plus 5, 3, 1, 1. But I claim a rearrangement of the bottom numbers doesn't change the distribution number, so it's very easy to see this is exactly 3 times 5, 1, 2, 2, plus 3 times 5, 1, 1, 3, like that. And that's just 3 times 5, 1, 2, 2 is 5 factorial over 1 factorial, 2 factorial, 2 factorial, and then we have 3 times 5 factorial over 1 factorial, 1 factorial, 3 factorial. 5 factorial is 120, and we're dividing it by 2 times 2, which is 4. 120 over 4 is 30. So we have 3 times 30, plus 5 factorial over 1 times 1 times 6. 120 over 6 is 20. We have 3 times 20. That's 90 plus 60, or 150. So we see that there are exactly 150 distributions of 5 distinct balls into 3 distinct boxes that don't leave any box empty. And you should always remember to compare this to the total number of distributions of 5 balls into 3 boxes with no conditions. That's just 3 to the 5th, which is 243. So you see we have many fewer when we exclude all of the ones that leave an empty box. Here's a question. Can we kind of generalize this? The answer, of course, is going to be yes, but it's not going to be quite so easy. In order to generalize it, we're going to have to give a new name to things so we can talk about them more easily, and these will be called the T numbers. We denote by TMN this number of ways to put M distinct balls into N distinct boxes. I'll say distribute M distinct balls into N distinct boxes with no box empty. And to use the method we used before, we just have to look at all the allowable types of distributions and add up their distribution numbers, which count the number of distributions of that type. Well, what makes an allowable distribution? An allowable distribution is one where the sum M1, that should be M1, plus M2, plus M3 up to M sub n, is equal to M. In other words, the number going into box 1 plus the number going into box 2, all the way up to the number going into box n, is M, the total number of balls. But also, no box can be empty, so each of these numbers, M1, M2 through M sub n, must be greater than or equal to 1. Now, in general, it's going to be hard to actually know exactly how to write down this complete list of all the allowable distributions. So instead, I'm going to use a kind of abstract symbol here, just this summation symbol, where I'm summing over all the possible distributions that meet these two conditions. All the good ones, all the ones that leave no box empty. And what am I summing for each such good distribution? I'm summing the distribution number, M on top, M1, M2 through Mn on the bottom. So the sum of these distribution symbols over all good distributions gives us the T number, TMN. And so in the book, they call standard problem 13 the problem of counting exactly this, the number of ways, the number of distributions of M distinct balls into N distinct boxes with no box empty. So that's standard problem 13, and the answer is exactly TMN, which is given by this formula. Now, I say this formula is not a closed form formula. It has the summation sign, and in this case, it's not even exactly clear, without in each case checking carefully that you've got them all, what you're summing over. You're summing over all possible types of distributions that meet these two conditions listed, but it is a formula nonetheless. And in the book they have what we call standard problem 14, how many words are there of length M from an alphabet of size n? And we saw already in the previous lectures that's the same problem here. Here we want to count words if each letter must occur at least once in the word. I claim that's the same problem as standard problem 13, just in a different form, because just like before, if you have a word of length M, you can think of these as balls number 1, 2, 3, up to M. The positions of the letters are like the balls. And the letters here are the boxes, A1, A2 through A sub n. So I'm labeling n distinct boxes by the letters A1 through AN. And if I want to count words that are made with these letters, putting in these positions, and each letter gets used at least once, it's just like putting the balls into the boxes, the position numbers into the boxes. Once you put the position in the boxes, that tells you what letter goes in that position, and you've created a word, and vice versa. So the answer, just like the answer to standard problem 13, is just TMN. There's this one-to-one correspondence between words with no missing letters and distributions with no empty boxes. Let's talk about some important special cases. What is TM1? This is the number of M letter words from a one-letter alphabet. Where you use that letter at least once. Well, of course, how do you make a word from a one-letter alphabet? You just put that letter in every position. So the answer is just 1. What is TMM? It's the number of words of length M from an M-letter alphabet. With each letter used at least once. Well, that's the same as just a string of length M with no repetitions, from an M-letter alphabet with no repetitions. You use each letter exactly once. You could think of that as the rearrangement of the letters A1 through AM. It's easy to see that there are M factorial such strings. Now here's where things are a bit tricky. There's one of the homework problems that I'm going to be asking you to do, which is to find a nice formula for TM2. In fact, they give you the formula. The formula is 2 to the M minus 2, which might seem a little bit strange, but the homework question asks you to give a combinatorial explanation for this. Is there a way you can count distributions of M balls into 2 distinct boxes, M distinct balls into 2 distinct boxes, where no box is left empty? Is there a way you can count that and see that it should always be exactly 2 to the M minus 2? Also in that same homework problem, you're asked to find the formula, or show that this is the correct formula, I should say, for Tm comma M minus 1. That formula is just M choose 2 times M minus 1 quantity factorial. And so the question is, can you give an explanation for why, if you want to put M balls into just M minus 1 boxes with at least one ball in each box, there are exactly this many ways to do it. So I'll state the results there. The homework question asks you to justify it combinatorially, and I want every one of you to really think hard about why these are the correct numbers. I'm writing them down here now because we're going to need them for the next lecture.